So this is the problem what we have. There's an arrangement. So there's a bar ABC is rigid and is supported by a steel cable. Okay, there's a steel cable, and the other end is a hinge. Okay, you can have a hinge. A is a hinge. B is the point where it is supported using a cable, and this is a rigid rod. Okay. Calculate the largest load P that can be applied at point C. So this is the load P. If the permissible stress in cable is limited to 40 megapascal. So this cable can take a maximum stress of 40 megapascal. That's what is said in the problem. And along with that, we need to calculate the vertical deflection at point C. So how much this particular point will be deflecting. Okay, because of this load, it will be deflecting downward. What is the maximum deflection what we are going to get? That's the problem that we have in our hand. Now, when we get such a problem, okay, the first thing what we need to think about is what is the force that is going to come in the cable in terms of P. So when I apply a force P here, what will be the force that will be coming in this cable? That is the first thing that we need to calculate. So if you're considering this particular ABC as a beam, how many reactions are there in the system for ABC? Or if I'm trying to plot the free body diagram of ABC, what are the external interactions? So this is a hinge. So we know that a hinge can have two reactions, right? One horizontal reaction and one vertical reaction. And here, this particular point B is connected to this cable. So this cable is also going to offer resistance to the downward movement. If this cable is not there, because of this force, it will move down. So this cable is also going to exert some amount of force, right? And I'm calling that as tension in the cable T. Okay, tension in the cable, I'm calling it as T. So these are the different forces acting in the system. There will be a tension in the cable which will be trying to restrict the motion of this particular point B downward. Similarly, there will be reaction at the hinge. Now let's use the basic equations, the concept from the first principle, that is sigma Fx equal to 0, which is going to give me HA equal to 0, because the only horizontal force in this system is HA, so that has to be 0. Now if I write sigma Fy equal to 0, I'm going to get it as VA acting upward, T acting upwards, and there is P which is acting downward. So minus P equal to 0. So VA is equal to P minus T. Now, there are three unknowns, so we need three equations, and the third equation is sigma n. So in this particular case, I will be considering A as the point about which I am taking the moment, because there are two forces. So these two forces will be having lever arm as 0. So the best thing to consider is taking moment about A. So what I will be getting is that this T is going to generate some moment. T times the lever arm, which is 2. So I'm going to get T times 2, and T times 2 is going to create an anti-clockwise moment. Okay, this is going to make this portion AB rotate clockwise. Hence it is minus. And then there is P, the lever arm will be 5 meter, and it is going to make this beam rotate clockwise. So plus P times 5 equal to 0. So from this equation, we can get the value of T. T is equal to P into 5 by 2, which is 2.5 P. I got the value of T in terms of P by using the first principle or the equations of equilibrium. So what will be the value of VA? VA is going to be P minus T. P is P itself. T is 2.5 P, which means I'm going to get the value as minus 1.5 P. The minus indicates that this reaction is actually downward. I assumed it upward and I got a negative value, which means this is actually a downward reaction. So I have the force in cable in terms of P. Now in this problem, the maximum permissible stress in the cable is given. And we know that stress is equal to force by area. Okay. And the stress need to be limited to 40. 40 megapascal means 40 Newton per mm square is equal to the force in the cable is 2.5 P. So 2.5 P divided by area. Area of the cable is given as 0.5 centimeter square, which is equivalent to 50 mm square. So directly from here, I'll be getting the value of P. So P is going to be 800 Newton. Okay, I got the value of P as 800 Newton. So that is the maximum possible force that you can apply at this particular point so that this cable won't be snatching off, this cable won't be breaking, because any stress greater than 40 will make this cable fail. So applying 800 Newton is going to create the stress 40 megapascal in the cable. So we got the value of P. Now the second part of the problem is the calculation of the vertical deflection at C. So we want to know how much this point will be deflecting. Okay, this point is going to deflect downward because of the application of the force. And we want to calculate this particular value. I'm calling it as delta C. So in the problem, it is said that ABC is a rigid member, which means that ABC won't be having deflection or it won't be having bending. So basically means that this member will be deflecting like this as a straight line. That is the importance of this rigid bar. Rigid bar will be moving as a single unit. Okay, so we can see here this particular point is having a deflection. I'm calling it as delta P. Okay, this particular point will be having a deflection delta B. This particular point will be having a deflection delta C. Now, what will be delta B? What will be delta B? Delta is the deflection at this point, which means it is actually the elongation of this cable. This cable is subjected to a force 2.5 P, and because of this 2.5 P, this cable will be deflecting and that deflection will be equal to delta B. So I can write delta B is equal to 2.5 P, or I can write it as T, the tension in the cable, multiplied by length. Length of the cable is 4 meter. It is given in the problem. So 4 meter, that is 4000 mm, divided by area is given as 0.5 centimeter square, which is 50 mm square, times the modulus of elasticity of steel, that is 2 times 10 raised to 5. This P, we already got the value as 800. On substituting all these values, we are going to get it as 0.8 mm. Okay, the deflection delta B is equal to 0.8 mm. Now here is the now we need to use the basic principle we learned in school, the principle of similar triangle. So what we have here is the undeflected member ABC. Okay, this was the earlier member, and after the application of the load, it got deformed. Okay, it got deformed like this. Okay, and this particular value, okay, this particular value is our delta C, and this particular value is our delta B. The length are given. This is 2 meter. Okay, so 2000 mm, This is 3 meter, which is 3000 mm. Now I can use the principle of similar triangle. The value of delta B we got it as 0.8 mm. So applying the principle of similar triangle, delta B by 2000 is equal to delta C by the total length, that is 5000. The principle of similar triangle, which means that delta C is equal to delta B, which is zero point 0.8. So 0.8 times 5000 divided by 2000. On doing this calculation, I'm going to get it as 2 mm, and that's the value of delta C. Okay, so here they have asked us to find two things. One is the value of P that we got, it is 800 Newton. The vertical deflection at point C that we got here as 2 mm. So that's how we solve this particular problem.